Hey everybody, this is Larry. This is day 16 of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord while we go over today's problem, longest mountain away. Okay, so a mountain is, there's a mountain top and then it goes over, okay, and then we have to find the longest one. Okay, one pass over one space, okay. I don't know if I'm going to do the one pass one, but I'll do the over one space one. So I think I've looked into similar problems before, but I'm not sure about this one. So we'll try our best. But the idea is that, so I have an algorithm that I'm thinking of, which is actually very good. It's a very good exercise in practicing amortized analysis. So I'm going to do that. So my algorithm is going to be, we look at for a mountain top. And when we found mountain top, we just go left and then the right to go to the mountain, right? So let's code that up and then we'll go over the complex and why that works. Because naively, you may think, okay, but that may be n square, right? Because you look at every mountain top and then, you look at every other element, that could be n square. So we'll go over that and we'll go over, everything in a little bit. But yeah, let's go to, let's try that out. Top index is equal to 0, current index none, doesn't really matter. Maybe I could do that later. But for top index in range sub n, where n is equal to length of a. Okay. So if I guess technically the mountain top could be in the front. Right? Is that true? I guess so. Oh no, I has to be okay. So I has to be not the first two index. Okay, just wanted to make sure on the ranges. So let's modify our for loops to make sure that's true. Okay. So now if a sub top index is greater than, strictly is it in this one? Okay, strictly greater than a of top index minus 1, and also it is strictly, now we have a mountain top, right? Now top index is a mountain top. Okay, and what does that mean? And then now we can try to go left as much as possible and then right as much as possible, and that's what we're gonna do. So left index is equal to top index minus 1, while left index is greater than or equal to 0, and a sub left index is less than a of top index left index minus 1. We do the same thing for the right index is equal to top index plus 1, while right index is less than n, and a of right index is less than a of top index. This is actually, I have to change this a little bit. I got that wrong on the right one, and you'll see why in a second. Oops, this is plus 1 as well. So this is actually left index plus 1, and this is right index minus 1 to kind of keep that monotonic, to keep it in descending order, right? Yeah. Okay. Let me know if that's okay. And then now we can choose, we have a best variable just to kind of keep track of things. Best is equal to max of, if there's no mountain, okay. Just wanted to make sure. Max of best, and also right index minus left index plus 1, I think. So yeah, and then return best. So second, okay, there's a 2, 2, 2, 2, 2, 2. Maybe the plus 1 as well. Well, the 0 is right. All right, let's see. Maybe let's do some debugging just to see if I'm off by 1 or something like that. Okay, so 3. So it thinks the 7 is the top, which is right. It goes to 0. Oh, I see. Because now the left index is it's not the index in which it is different. It is the index which is it is less than, right? So this should be it's a little bit weird with the off by ones on the border, so I have to figure it out. So I think what I would do instead, do I want to just pad A, or there are a couple of ways to handle it, but yeah, we can just do total is equal to right index minus left index minus 1, because this is a little bit weird, but to kind of fix the off by ones, but that's okay. But basically this is not including left index or right index, and then now we can kind of fix it by saying if a of left index is less than a of left index plus 1, then total increment by 1. If a of right, this is a little bit hacky, we could probably do another way of cleaning this, but for now that's not what I want to focus on, something else. So yeah, so let's kind of take a quick look. Okay, that looks good. Let's give it a quick let's see what happens here. Just want to double check a few things, and we have to make sure that okay, length could be 0. That's awkward. Oh yeah, I have to that's actually intentional, but wait, what? Oh wait, because right indexes could be n. Okay. Okay. And also let's try those empty cases. Okay, looks good. Let's just try one with many mountains. And I think if this is good, I'm confident in submitting. Let's give it a quick submit, and hopefully I don't have any off by ones. Okay, cool. So you may ask yourself, right, like I said at the beginning of the video, which is what I want to focus on, even though there are other things you can talk about, is but for complexity analysis, right, you may say, well, there's a for loop here, and that's O of n, and there are while loops that goes all of them, right? So that's going to be n squared, and that's a possible bound, keeping in mind that O of n squared, or sorry, O of n is O of n squared as well, if that makes sense. In that's how big O notation kind of works, right? But so it doesn't have to be a tight bound. So what I mean by that is that okay, so how do we figure this out? This is actually linear time, right? Okay, so I would say two things. One is, let me skip ahead a little bit, is that for space complexity, we're doing O of one space because, well, we only have a couple of variables, right? So it's O of one space. I hope that part is obvious. I just want to get that out of the way. And then for time complexity, this is O of n, because if you look at, let's ask ourselves how many questions, right? How many indexes can be the mount top, right? Well, maybe O of n, say. O of n is probably roughly n over 2-ish, give or take 1. But then how many non-mountain top can be, was it cells maybe? Spots can be visited, right? Well, we visited once to do this check, and then we visit once from the left side to do this check from a possible mountaintops, and then a possible mountaintop from the right side, right? That means that, for example, let's say you have this number. I mean, a variation of this example, where let's say you have, let's say you just have like this, right? Something like that. And then so another way to look about this problem is that, let's say you have this really long answer or long array, and you're looking at how many times this can be accessed, right? Well, oh, this is actually a mini mountaintop, so maybe that's a bad example. But let's just make this 1 and 0 so that it's lower, right? Let's say, yeah, how many times can this 1 be accessed, right? Well, you're gonna access it once to do this check to see if it's a mountaintop. That's 1. You're gonna check it from the left side because the 7 the amount top is going to go 7, 3, 2, 1, and so that's the second time. And then the third time is from the right side, right? Where well, okay, that's not the case in this case. Magic. From the 7, you go, okay, this is a mountaintop. So let's go do. And this is at the bottom, right? So that's the third time. In any other case, like let's say this one now, or right, you're not even going to get access on the right side. So basically, each cell or each array spot will get only accessed at most 3 times, so constant number of times, right? So that means that looking backwards instead of looking at forwards into how much the loop does, you look at how much each spots in the cell will get accessed and math stuff done on, and there's constant amount of time. And since we have constant number of time and linear amount of cells or spots, then together it makes linear time. I hope that's understandable. This is technically not one pass, I don't think, but I don't think it's that interesting anyway. And I think you could do some maths on like going up and down or something like that to maybe do it. But because I think you could prove that. I think another way to do it is actually that you could prove that a mountaintop always starts at the bottom. Or sorry, a mountain always starts at the bottom, because if it doesn't, then let's say you want to try here. Well, why wouldn't you start it here in a greedy kind of way, right? So you could start here and then go all the way to another bottom. So basically, you're just measuring the distances between the bottom. And I think that's easier as well. But I wanted to use this that's easy anyway. But I wanted to use this opportunity to do it this way to show the amortization of how this is linear time, even though they're a for loop and 2 while loops, even though they're not nested. So yeah, let me know what you think. Let me know how the explanation goes. Let me know if you found the other one pass solution, which is just find bottom of mountains, I guess, right? And I will see y'all tomorrow. Bye bye.